We will continue our discussion on IC engine, and today we will discuss about octane number, Cetane numbers, and we will discuss about fuels, I mean and alternative fuels like methanol, ethanol, hydrogen, natural gas, etc. Before I go to discuss about octane number, Cetane number, let us first discuss about another one numerical problem that is related to thermochemistry. So, we have discussed about that what is the thermochemistry and the chemical reaction. I mean, we have seen that actually fuels are basically a family of hydrocarbons. So, depending upon the number of hydrogen atom and carbon atom, whenever we use a particular fuel for the combustion, all the carbon will be converted to carbon dioxide, hydrogen will be converted to H2O, and there requires stoichiometric oxygen. That amount will be good enough to convert all the carbon into carbon dioxide, hydrogen into H2O, and there should not be excess oxygen, so that we may get NOx and CO. So, we need to know that what will be the stoichiometric or chemically correct amount of oxygen required to burn a particular fuel, I mean when it is used in internal combustion engine, and that information is obtained from the thermochemistry of the fuel. So, today we will work out an example to know that what if a particular hydrocarbon is given a generalized formula CXHY, then how can we calculate the amount of oxygen required to burn that fuel to have an efficient combustion. That means there will be required amount of oxygen only, there should not be no excess amount of oxygen, and to get that amount of oxygen, what will be the amount of air required, and that will be supplied to the engine, and that we will come to know from the problem. In fact, we have solved one problem while I was discussing about carburation, and there we have seen that what is the air fuel ratio or fuel air ratio. Then we have discussed that take an example of a fuel. We have discussed that what will be the amount of oxygen required to burn that fuel, and that much amount of oxygen will come from a certain amount of air. So, then we have calculated the fuel air ratio and vice versa. So, today we will work out one example for the thermochemistry, that is combustion reaction, So, basically thermochemistry of the fuel. So, we will now write the problem. It is very important. So, if a fuel, a hydrocarbon fuel, I am writing the problem. A hydrocarbon fuel is expressed as CXHY. Write the stoichiometric equation for this fuel. The fuel, it is also given, the fuel contains 84% by mass, 84% by mass of carbon and 16% by mass of hydrogen. Determine the stoichiometric air fuel ratio. Determine the stoichiometric, or which is sometimes known as chemically correct air fuel ratio. As I said you that this will be obtained from the thermochemistry of the fuel, that a hydrocarbon is generalized expression, that is CXHY. So, the number of hydrogen atom and number of carbon atoms eventually dictates the amount of oxygen required, and if that amount of oxygen is required for the complete combustion or complete burning of the fuel, there should not be incomplete combustion. So, to burn that amount of fuel, if we require certain amount of oxygen, then what will be the adequate amount of air we need to supply per kg of fuel. That information is obtained from the combustion reaction, and that is what we have discussed. So, we have to solve this problem. So, this is the problem statement. So, we have to solve. So, now how can I solve that? It is very important. So, we need to write the generalized expression, rather a chemical reaction for the fuel. So, we will write first the combustion reaction or chemical reaction or combustion reaction taking this fuel CXHY. This is the most generalized expression, that is why I have taken up this example. So, instead of CXHY, if the hydrocarbon is given by formula, then it would be much easier. So, CXHY is the fuel. So, if I write the combustion reaction, of course, it will be acting with oxygen, then it will produce carbon dioxide plus H2O, and this reaction is basically exothermic reaction. So, it generates huge amount of heat. So, now we need to know that for the complete combustion, that means all the carbon atom will be converted to carbon dioxide and all the hydrogen atom will be converted to H2O molecule. So, for that, how much amount of oxygen required, that information will be obtained from this reaction, and knowing the amount of oxygen, knowing the required amount of oxygen for this particular fuel to have complete combustion, we can calculate the amount of air needs to be supplied for that to the engine for the complete combustion. So, if I like to balance this reaction, then probably I can write this is X CO2 and this is Y by 2 H2O. Then if I would like to obtain all carbon, if all carbon converted to carbon dioxide and all hydrogen converted to H2O molecule, then probably the amount of oxygen required, it will be X plus Y by 4. This is the reaction. We need to calculate first the amount of oxygen required. It is given that the fuel contains 84% by mass carbon, by mass of carbon, and 16% by mass of hydrogen, right. So, H, then so what I can write, that as I said that all carbon will be converted to carbon dioxide. So, mass ratio, if I calculate mass ratio, then 12 plus 32, it is getting 44, that is the molecular weight. So, what I can see from this reaction, so if all the carbon is converted to carbon dioxide, then I can see from this reaction that 0.84, we can see that 12, okay, I am writing next slide. So, we can see from this reaction that 12 kg of carbon needed, how much, 32 kg of 32 kg of oxygen, then 44 kg of carbon needed, 32 by 12 into we required 84% by mass. So, 0.84 kg of oxygen. So, this is coming out 2.24 kg of oxygen required if the fuel contains 84%, that is what I have described, that 84% by mass of carbon. So, that means for 0.84 kg of carbon needed 2.24 kg of oxygen to convert all the carbon atoms into the carbon dioxide. Similarly, if I write the reaction for hydrogen, then twice H2O plus O2, it will be twice H2O. That means 4, it is 32 and we obtain 36. So, from this reaction we can see that 4 kg of hydrogen needed 4 kg of hydrogen needed, 4 kg of hydrogen needed, 32 kg of oxygen, and then therefore we can calculate that 1.6 kg of hydrogen will be needed 32 by 4 into 0.16 kg of oxygen. Therefore it is coming out 1.28 kg of oxygen. So we have obtained the amount of oxygen required for the conversion of all the carbon atoms and hydrogen atoms into the CO2 and H2O. There will not be, so what is the amount of oxygen required? So that means the total oxygen needed is 2.24 plus 1.28, that is 3.52 kg. So we require 3.52 kgs of oxygen for the complete combustion. That means all the carbon atom will be converted to carbon dioxide, all the hydrogen atom will be converted to H2O molecule. There should not be any excess oxygen, so that carbon dioxide again further can react and it may create CO2, and we may have NOx and carbon monoxide. So we have identified the amount of oxygen required for the complete combustion. Now we need to know that what will be the amount of air required to obtain this amount of oxygen, because we will get oxygen from the air supplied to the engine. So the total air needed, because we know that air 1 kg of air contains how much kg of oxygen, that is very important, that we need to know. So that information is very important, that what will be the amount of oxygen required for the complete combustion, or that is stoichiometric air fuel ratio, because without this information we cannot calculate. So 1 kg of air contains 0.232 kg of oxygen. So we know that if I supply 1 kg of air, then we will get 0.232 kg of oxygen. So to obtain, because we have calculated the, then that means therefore total amount of air needed for the complete combustion will be 0.23 kg of oxygen available from 1 kg of air. So we have calculated that 3.52 kg will be obtained from how much amount of air. So we can calculate that 0.232 kg of O2 is obtained or available in 1 kg of air. Therefore we can calculate that 3.52 kg of oxygen is obtained from 3.52 by 0.232 kg of air, right. So then we can calculate what will be the air fuel ratio. So we know that, so this will be the air fuel ratio or fuel air ratio, that is very important. So 3.52 divided by 0.232 is the, this is known as the, so for 1 kg of burning of the fuel we require this kg of oxygen. So we can calculate air fuel ratio. So air fuel ratio will be 3.52 divided by 0.232, that is near about this will coming like this 15.1. So we have calculated that the stoichiometric air fuel ratio, that is 15.1:1. So this is the stoichiometric air fuel ratio that we have calculated. So we have obtained the amount of oxygen required for the complete combustion, and then we have calculated that to obtain that amount of oxygen, how much amount of oxygen how much amount of air need to supply. That means that means per kg of burning the amount of oxygen, amount of air is required is 15.1. So, the air fuel ratio will be 15.1. So, with this we have seen that by how we can calculate the required amount of the stoichiometric amount of oxygen or chemically correct amount of oxygen should be supplied for the complete combustion of a fuel having a generalized formula CXHY, and probably it will give you a clear picture that how we can calculate from a combustion reaction, that is from a thermochemistry of a fuel to have a efficient combustion. Okay. So, next we would like to discuss about very important aspect is that self ignition characteristics and octane number. So, it is very important that self ignition characteristics of fuel, and from there we will discuss about octane number and cetane number, very important. So, what is self ignition characteristics of the fuel? So, that means we have seen that in case of a internal spark ignition engine or I mean even for the compression ignition engine, you have seen that if the temperature of an air fuel mixture is high enough, then mixture will self ignite. Rather, I mean in case of a spark ignition engine, we require an external agent like spark plug to ignite the fuel, but somehow if we can raise the temperature of the air fuel mixture that is being supplied through carburetor to a level, so that without it will self ignite, rather it will burn without needing an external agent like spark plug or source. So, the temperature above which this occur is known as self ignition temperature of the fuel. So, what I am telling that whenever I am using any particular fuel in a spark ignition engine, or in case of a I mean we do not require any spark plug or external agent for the compression ignition engine, because compression ignition engine itself, in a engine the high pressure and temperature, rather high, the condition of the air at the end of the compression itself allow the fuel to be self ignite. So, the temperature itself is so high that whenever fuel is sprayed through a fuel nozzle, the air fuel mixture self ignite. Now, in case of a spark ignition engine, we supply air fuel mixture through carburetor, then at the entire mixture is getting compressed during the compression stroke, and at the end of the compression stroke we need to switch on the spark plug, and the spark plug will ignite, rather it will ignite the mixture, rather combustion will start from there. And we will discuss one day about the combustion in SI and CI engine, and we will come to know that combustion start from the zone which is close to the spark plug. Now, now I have said that somehow if we can raise the temperature of the air fuel mixture that is being supplied in the into the engine cylinder. So, if we can raise the temperature by increasing the compression ratio, but by increasing the compression process to an extent that without needing any external agent like spark plug or source, the fuel mixture will self ignite. The temperature above which it occurs is known as the self ignition characteristic of the fuel. So, I am writing that if the temperature of the air fuel mixture is high enough, becomes high enough, if the temperature of the air fuel mixture becomes high enough during the compression stroke, during the compression process, the mixture that is air fuel mixture will self ignite without the requirement of spark plug, which is an external agent, or any other source or any other sources. So, we have seen that the temperature, if we can raise to a level that we do not require any external agent to ignite the fuel, and this is very important, and the temperature of the mixture, the temperature of the mixture above which it occurs is known as the self ignition temperature of the fuel. Sometimes it is known as SIT. So, that means the temperature above which it occurs is the self ignition temperature, I mean, this is the basic self ignition temperature of the fuel. The basic principle of ignition in a compression ignition engine, the compression is high enough that this is of course for SI engine. So, this is I am talking about for SI engine, right. But as I said again, for the compression ignition engine, the temperature of the mixture, is high enough, and high enough that the temperature go above the self ignition temperature, go above the self ignition temperature of the fuel, and then ignition occur when fuel is injected, when fuel is spread through nozzle. So, here the temperature is always above the self ignition temperature of the fuel. So, it do not require any external agent for to initiate the combustion. That is what we have seen. Now, question is, if I try to draw the temperature versus time, very important. Now, if I try to draw the self ignition characteristics of the fuel. So, if I try to draw that self ignition characteristics of fuels. So, if I try to draw, very important, that time versus. So, if I take time along x axis and if I take temperature along y axis, then what I can see from the graph that we will discuss now. So, if we take time as x axis and temperature y axis, suppose if I take a particular fuel, so whose self ignition temperature is having a fixed value. So, this is the self ignition temperature of a particular fuel. So, this is the self ignition temperature of a particular fuel that is fixed. Now, question is, if I increase so during the compression process we are increasing the temperature, maybe we are increasing in such a way that, so we are increasing the temperature. Now, if the temperature is, so if I draw the temperature and temperature is less than the self ignition temperature, if the temperature less than the self ignition temperature, so here temperature rise is less than the self ignition temperature of the fuel. So, here we do not have any self ignition. So, it will be always cooled off, I mean mixture will be always there is I mean no self ignition will occur. I mean since the temperature rise during the at the end of the compression stroke, at the end of the compression stroke is less than the self ignition temperature. But so this is compression heating, of course. So this is rise in temperature during compression stroke. Now if I increase the self ignition temperature and then right, this is known as, so this is I will tell. So even if I rise the temperature above the self ignition temperature, we can see that immediately after, whenever temperature reaches just above the self ignition temperature, combustion may not take place, but entire combustion will require certain amount of time, as there will be required a finite amount of time for the complete combustion. And then again we can see that this point is combustion completed and drastic rise in temperature, and so the moment when the temperature go above the self ignition temperature, then entire combustion is not completed, maybe fuel by mixture, self ignition has already been started within the mixture. Now question is, we require certain amount of time for the complete combustion, and then only you can see there is a drastic rise in temperature, the certain amount of time which is known as ignition delay of the engine. So this ID which is known as ignition delay of the, this is known as ignition delay. That means mixture will cool off, the mixture will remain, the mixture will cool off when the self ignition temperature is less than temperature is less than SIT, that is mixture will cool off, no combustion. If the self ignition temperature, if the temperature go beyond the self ignition temperature, even then we can see from this figure that we require certain amount of time which is known as ignition delay for the complete combustion. That means that if the mixture is heated to a temperature, so that means if the, what is ignition delay? If the mixture is heated above the self ignition temperature, then self ignition will occur, I mean after a short time delay, which is known as ignition delay or ID. This ignition delay, I am writing this ignition delay or ID, it has two different parts. One is known as physical delay, it consists of two different parts plus chemical delay. So this ignition delay, the time required to self ignite after reaching the self ignition temperature, which is known as ignition delay, and this has two parts, one is physical delay, another is chemical delay. And as I said you that maybe whenever the temperature of the mixture reaches above the self ignition temperature, combustion may start or may initiate, but to complete the combustion we require certain amount of time, and then only we can see that the drastic rise in temperature is an indication of having complete combustion. So we can see that the time required from initiation of the combustion to complete of the combustion is essentially the ignition delay, we can say. So I have written the definition that the mixture is heated above the SIT, then self ignition will occur, that is fine, after a short time delay, which is ignition delay. But this ignition delay physically signifies that the time required from the initiation of the combustion to the complete of the combustion, and it depends upon several factors, and that is why I have written here that the ignition delay can be decomposed into two parts, one is physical delay, another is chemical delay. Physical delay, that is a time delay associated with the so many issues. That means whenever we are supplying, it will self ignition will occur, that is of course in the context of compression ignition engine. So we can't think about having self ignition in case of a spark ignition engine. So self ignition engine, that means self ignition, that means compression ignition engine. So it depends upon the total ignition delay. As I said you, there is a time required between the initiation of the combustion to the complete of the combustion. So maybe we are spraying fuel immediately after reaching the self ignition temperature. So it will take some time, nozzle will take a finite amount of time to supply the spray, because until unless we are getting desired spray pattern and desired fuel in all the places, we cannot have complete combustion. So that is associated with the physical delay, that is the time required to have a complete spray of the fuel or required amount of fuel that will be sprayed into the engine through the nozzle. And chemical delay, it essentially depends upon the chemical characteristics of the fuel, because as I said you that nozzle is used to fragments the droplet, as I have discussed in detail about it in my last lecture, one of my last lectures. So we have seen that we need to decompose, we need to fragment fuel into smaller and smaller droplets. So whenever combustion might start from smaller droplets and it will go to the next and next, and that essentially depends upon the chemical compositions and chemical characteristics of the fuel, and that is why we require certain amount of time. So maybe whenever we are supplying fuel and the smaller droplet or the first fuel droplet will take part in the combustion, then it will percolate in the next droplet. So we require certain amount of time to initiate the complete combustion, to complete the combustion in the entire domain of the cylinder. That is why it is known as chemical delay. So physical delay, that is the time delay associated with the supplying complete amount of fuel with a desired spray pattern in the combustion chamber, and chemical delay, that is essentially associated with the chemical characteristics of the fuel, that depends upon which hydrocarbon we are using, and maybe number of fuel droplets we are having, and maybe when one droplet is taking combustion is completed, it will percolate to the next droplet, like so. So it depends upon the entire chemical combustion. So we have seen that the ID is essentially a small time required that which indicates that the combustion is completed. Now question is very important. So now if I draw another figure again, so we can see that very important, that if we somehow can, this is important. So the higher the initial temperature rise above the so from there I can say I can write that if we increase the higher temperature rise, that is this is compression heating, that is the rise of temperature during compression, if it becomes higher, then we can see from the figure that the ignition delay reduces. So even though we are using the same fuel, we cannot really make it zero the physical delay and the chemical delay, but physical delay, but chemical delay we can reduce by increasing the initial temperature of the mixture. So we do not have control over the physical delay, because this is associated with the functioning of the nozzle itself. So what we can do, we can raising the initial temperature of the mixture to an extent, rather higher the initial temperature of the fuel mixture above SIT, lesser will be the ignition delay, and this less amount of ignition, the less time required will come from the fact that we require lesser amount of the chemical delay is getting reduced. So from this figure what we can see, that higher the rise in temperature, higher the rise of initial temperature, of mixture above self ignition temperature, the shorter will be the delay, So that means by increasing it depends upon many things, air fuel ratio, presence of gases, density, and so and the values of SIT and ID, and so higher the initial temperature of the mixture above the SIT, the shorter will be the delay, and that delay we will take into account the it's the sort of reduction of the ignition delay will essentially comes from the reduction due to the reduction of the chemical delay period. So, now this self ignition temperature as well as the ignition delay, this depends upon many things. What are the things? It depends upon temperature, pressure, right, temperature, pressure, many variables. It depends upon many variable, depends upon many variables, temperature, pressure, inlet swirl, then air fuel ratio or fuel air ratio, whatever it is, fuel air ratio, then presence of inlet gas, and finally turbulence. It is very important. We will discuss what effect this turbulence is having in the context of combustion, that we will discuss. So, these are the different variables by which essentially dictates this self ignition temperature, ignition delay of a particular fuel. Now, it is very important is that, so we have seen that in the context of SI engine, this self ignition temperature is very important, because it in a SI engine it won't compression heating won't allow the fuel to self ignite. So, we have seen, and that is why you require a spark plug. Now, we need to know another number, another numerical value which is known as octane number. So, what is octane number, right? So, I am writing the fuel property that describes how good a fuel will self ignite or not is called the octane number or just octane, right. The property that describes how good a fuel will self ignite or not is known as the octane number, right. So, this is a numerical value. So, this octane number is basically a numerical value. This is a numerical value. This is a numerical value. Is a numerical value, and we need to generate. So, this numerical value and the scale we need to generate by comparing the self ignition temperature of two standard fuels in a test engine at specific condition. So, we can experimentally generate a numerical value scale of the variable octane number. So, if we know the octane number of two standard fuels, and then if you would like to know the octane number of any given fuel, then we can take that fuel in doing test in a engine at a specific condition. We can generate this scale by how and what will be what are the two standard fuel. So, we have understood that in the context of SI engine, we do not know whether fuel will self ignite or not. In fact, fuel is not self igniting, that is why I require a spark plug. Now, what will be consequence if the fuel self ignite in a SI engine, that we will know. So, the octane number is basically it is a numerical value that describes how good a fuel will self ignite or not, and we need to generate the scale of this number, and for that if you need to know the octane number of two standard fuels, and then if you would like to know octane number of any other fuel, then we have to take that fuel in a test engine at some specific condition, knowing the value of the octane number to other fuels. So, these two standard fuels are used. Two standard fuels are very important. One is isooctane. I am writing isooctane, which is isooctane which is having octane number is equal to 100. Number 2, N-heptane. N-heptane, these are the hydrocarbon which is having octane number is equal to 0. So, these are the two extreme cases. So, by knowing the octane number of these two fuels, we can calculate what will be the octane number of any other fuel. So, this is very important that we can calculate, we can take that particular fuel in a test engine at specific condition, and from there we can calculate. I will give you the empirical formula from where we can calculate the octane number of any other fuel, knowing the numerical values of these two standard fuels which is having octane number 100 and 0 for isooctane and heptane. Now, question is, so if the octane number value is high, then octane number value is high, that indicates the fuel is likely to self ignite. So, engines with low compression ratio can be used, can use fuel with lower octane number. So, I am writing this octane number which is ON. So, higher the value of octane number, fuel is less likely to self ignite, That means the fuel which is having higher octane number, it is less likely to self ignite. So, if I now from this, if I can say that engines which are having low compression ratio, that is spark ignition engine. So, low compression ratio engine, because compression ratio itself is low. So, in those engines we will be using can use fuel with low octane number, So, spark ignition engine which are having normally low compression ratio will use low octane number. If they use higher octane number fuel, it is less likely to self ignite, because it won't self ignite. So, if we use low octane number, so they will having tendency to self ignite. Since we are having low compression ratio, compression heating is not so much. So, that means they have if we use even on the top of that high value of octane number, then their tendency to self ignite will be less. So, if we use low octane number fuel, their tendency to self ignite will be fuel. So, even maybe although we are having spark plug, but still the compression heating will itself allows the temperature to go close to the octane number self ignition temperature, so that they might have a tendency to have self ignition. Okay. So, this is about the octane number that essentially describes that how good a fuel will self ignite or not. So, today I have discussed about the octane number. We have discussed one problem. We have solved one problem to know the what is the amount of oxygen required through the combustion reaction. We have seen and we have discussed a problem taking a generalized expression of the hydrocarbon CXHY. Then we have discussed that what is the self ignition characteristic of the fuel, and then we have discussed about a few important things, what is ignition delay and by how we can reduce the ignition delay, and we have discussed that self ignition temperature and ignition delay depends upon many variables, and one of the important variables is the turbulence. We will discuss that aspect while we are discussing about the combustion in SI and CI engine. Then we have discussed about octane number, which is basically numerical value, and it is generated from a experimental investigation taking two standard fuel which are basically isooctane and which are basically isooctane and N-heptane, which are having octane number 100 and 0 respectively. So, if you would like to know the octane number of any other fuel, then we can take that fuel in a particular test engine at some, and we can carry out experiments at specific condition. And then finally, we have seen that octane number, if the value of octane number is higher, the fuel will have self tendency to ignite, that is fuel is less likely to self ignite. So, naturally the engines which are having low compression ratio, that means their compression heating is not that much, they should not use the octane number fuel of fuel having higher octane number. So they will try to use fuel with low octane number. So the compression heating may raise the temperature very close to SIT. So they may start self ignition even without the support of spark ignition, spark plug. So with this I stop here today, and I will continue my discussion in the next class. Thank you.